So now let's describe how these feature vector definitions can be used within the context of global linear models for dependency parsing. So recall that to run the perceptron algorithm, we need to be able to calculate this function, capital F of x. X is a sentence. For example, John saw Mary. And this function is going to take a sentence and map it to some dependency structure. For example, this structure here, John saw Mary. And it's defined in the usual way in in global linear models. Gen of x is defined as a set of all possible dependency structures for this input sentence. And I'm going to take a max over all possible structures. And we're going to score each of those structures using w.f, where w is a parameter vector. In d-dimensional space, and f is a feature vector. So again, as we saw in tagging, it's critical that we can compute this function capital F of x efficiently for a couple of reasons. One is when we get a new test example, we want to be able to parse it. We want to be able to apply this function. Okay. The second reason is that to run the perceptron algorithm that learns these weights w from examples, we need to repeatedly calculate this function on the training examples. Remember, the perceptron typically calculates the output on a particular training example under the current parameters, and then does a very simple update to those parameters if we make some errors. So f of x is crucial within the perceptron algorithm. And again, let's just emphasize this set gen is typically very large. So it's exponential in n, where n is the length of the sentence. As I've just shown you, we have defined this function capital F, lowercase f, the feature vector function, through a sum of local feature vectors. Each of these feature vectors takes a sentence and looks at just a single dependency within the structure y and returns a feature vector. So this problem here is reduced to the problem of finding the highest scoring structure in gen, where the score of any structure is through the sum of terms, one for each of the dependencies. Now, I'm not going to explain the algorithm for this. I'll try to post a paper which specifies the algorithm, but critically, we can make use of dynamic programming for this problem, and it actually runs in cubic time in the length of the sentence. And intuitively, that is because we've decomposed the score from an entire structure into a sum of local scores across just dependencies within the structure. And that decomposition allows us to use dynamic programming algorithms that are really quite similar to the algorithms that we saw for PCFGs. So they're similar to the CKY algorithm, but which leverage dependency structures in really rather beautiful ways. And again, Jason Eisner has some wonderful papers on these algorithms. So to summarize, we've defined our global feature vectors through local feature vectors. That allows us to find the highest scoring dependency structure under the model very efficiently using dynamic programming. We can use that dynamic programming method both within the perceptron algorithm when we train these parameters w, and also for decoding new test sentences. To finish up this segment, let me just talk a little bit about the kind of features that McDonald actually looked like. And they're very similar to the features I showed you. So remember, a feature vector is going to take a sentence, a head word, and a modifier word. So we'll define w sub I to be the ith word in the sentence, and t sub I to be the ith tag, so the part of speech tag for the ith word. So again, we're going to assume that as input, we don't just have the sentence, we also have the part of speech tags for that sentence, because the part of speech tags can give us valuable information. There are some very simple unigram features which just look at the identity of the head word, or the identity of the modifier word, or the identity of the head tag, or the identity of the modifier tag. More interestingly, there are bigram features, which are rather similar to the features I showed you on the previous slide. So we can look at the identity of the for tuple, WH, WM, T sub H, T sub M. So we could have features which are true for a particular combination. So maybe SOR, John, VBD, NNP. So we'd have a feature which is 1 if and only if we saw a dependency between a word SOR tagged as a VBD and a word John tagged as an NNP. And we can also define features which look at various subsets of this for tuple. For example, we might just look at the two words involved. We might just look at SOR and John, or we might just look at the two parts of speech involved, or we might look at just the fact that we have John tagged as an NNP modifying some VBD, and so on. MacDonald also used contextual features. For example, you might look at not just the tag if we have a particular dependency. So this is word H and this is word M. You might be interested not just in the part of speech tag for this mth word and the part of speech tag for this hth word. You might also look at the part of speech tags to the immediate left and right of this head and modifier word. So for example, we might look at the for tuple th plus 1, so that's this part of speech, and then tm minus 1 tm, so this part of speech and this part of speech. And there are several kinds of features you can define here which look at the part of speech of the modifier word and the head word, and also the part of speech of the previous word or the next word for each of these cases. So that clearly gives us a richer context in which to consider a particular dependency. Finally, an important class of feature are what are called in-between features. So empirically, we are, or statistically speaking, some parts of speech, for example a verb, cause a dependency to be relatively unlikely. So if a verb is seen between these two words, that diminishes the probability of seeing a dependency. So it seems empirically, if you look at least English, the chances of it seeing a dependency crossing certain parts of speech, such as a verb, is much less than chances of crossing other parts of speech. And so MacDonald introduced features which would track the tag of the head, the tag of the modifier, and also would check whether a particular tag, for example VBD, was seen between these two words. So this turned out to be another useful feature type.